Okay. So let's talk about this. So when we did the slopes, we got y equals negative 3x plus 2, and the result was the horizontal line, which was y equals negative 3. Why does that make sense? Why did it make sense that we ended up with a horizontal line when we did the slopes of that linear function? What did we say last week? Yeah, so it's like the constant slope. We had a constant slope, which makes sense that all of the slopes would match. All of the difference quotients were equal. Okay, and so then we did x squared and x cubed, and our derivatives became 2x and 3x squared. So just kind of looking at those patterns, all right, for those three, remember the equation of that line would be the same thing as f prime of x was negative 3. What do we think? What's your best guess in terms of what the derivative of x to the fourth might be? It's okay if you're wrong. What do you think? 4x to the third. That's actually 100% correct. Okay, 4x to the third. So if we're just looking at the other patterns, started with a quadratic x squared, it became 2x. Started with a cubic x cubed, it became 3x squared. Started with a quartic x to the fourth, it became 4x cubed. If that's the case, what do we think about x to the 50th? Well, what power would x be? 49. What's my coefficient going to be? 50. Okay. So what is it? Well, I guess I should follow this. Okay. What does it seem like we're doing every time? Yeah, it looks like the degree goes down 1. Degree goes down 1. Degree decreases by 1. And then how do we get the coefficient? All right, we multiplied the original coefficient by the original degree. Okay, I would agree. It looks like that's what we're doing every time. Okay, so that's the case. Let's talk about some transformations. Okay, so now let's take that quadratic and we're just going to scoot it up 6. Okay, so well, I just told you the answer. The transformation was we went up 6. Okay. What do you think dy dx, or the derivative, will still be? It will still be 2x, okay? How do we know that? What do you think? Yeah, it does not change the, that transformation doesn't change the shape of the function, right? So because that transformation does not change the shape of the function. Okay, so then what's the transformation for y equals 5x squared? What happens when we put a coefficient on a function? What's the transformation? It's a stretch, right? It's a vertical stretch. Good motions there, Wilbur. I knew what you were saying.
Sorry.
It's all good. Okay. It's a vertical stretch. Well, if that's the case, all right, what's dy dx going to be? 10x. Okay, so using our pattern that we had a few minutes ago, it changes that derivative a little bit. Okay, it changed the slope of the derivative, right? So the transformation changed slope of the derivative, or changed the slope, okay, of our curve. Now, if we think about, back up there, that transformation of up 6, okay, if I think about the number 6, if I think about it as just y equals 6, right, what does that look like if I graph y equals 6? It's a horizontal line. What would be the slope of any horizontal line? 0. Okay, so that's why a transformation of up 6 doesn't change my derivative, okay, because 6 is a constant. All right, so now let's do some best guesses, all right? So if our function gets more complex, so negative 19 x to the third plus 4x minus 3, what's your best guess for j prime? That is 100% correct, okay? And then if we evaluate j prime at 6, what value did y'all get? Negative 2048. Okay. Then it says, hey, use Math 8 on your calculator. All right, to verify it. Were you correct? Yep, you sure were. Okay, so we put our original j function in there on Math 8, and we should get the same thing. Okay, so looking at all these properties, looking at what we've done so far, let's mess with this chart that's down here. Okay, so it gives me a few that have already been done. Okay, I would tell you to save 7. All right, to the end, but see what you can do with 8 and 9. See if you can find the derivative based on the patterns in the chart and the things that we've been doing. Okay, do your investigation. Take a second and work through that. Let's try 8. Okay, I think 8's the most straightforward. All right, so let's walk through it. What would its derivative be based on everything we've been seeing? What would the first term be? Yep. What would the second term be? Yep. And the next term? Yep. And the last term? Negative 8. Okay? So negative 8, I agree. That's what we've been doing. All right? Let's look at the one beneath it. All right? So you got some negative exponents. Not a problem. We just have to think about what we would do there. Okay? What's that first one going to be? Follow your same pattern. What have you been doing? Negative 9. X to what power? Negative 4. Okay? Because each time we're subtracting 1 from the exponent, right? And if it's already negative, it's going to make it more negative. Okay? So negative 9, x to the negative 4th. Good. All right? The next term, 8x to the negative 2. My coefficient's going to be negative 16, but x is going to be to what power? Negative 3. Okay? Then we switch to negative 7x. So I would get a negative 7. X would go away. It'd be x to the 0. Okay? So interesting there, right? If it's a negative exponent, it's going to get more negative because we're subtracting 1. All right, let's do those fraction exponents. Okay? We love fractions. Said no one ever. All right, so here we go. All right? So 2/3. I would multiply that by my original coefficient, which is 1. So what's my new coefficient going to be? 2/3, okay? I'm going to subtract 1 from 2/3. So 2/3 minus 1 would give me what? Negative 1/3. Okay? So 2/3 minus 3/3 would give me a negative 1/3. The next term, 1/3 times 3, that would be 1. And then 1/3 minus 1, or 1/3 minus 3/3 would give me what power? Negative 2/3. Derivative of a constant minus 8 would be 0. It had no x term there. Okay? So let's talk about what we did. All right? This is what we said. We multiplied the coefficient by the original exponent. And then subtracted 1 from the original exponent. Okay. That's exactly what we did. Okay, we took the coefficient of the, multiplied the coefficient by the original exponent, and then we subtract 1 from the original exponent. We keep the variable. Okay. Does that rule explain why the derivative of a constant is going to be 0? So let's think about that for a second. Okay. If f of x equals, let's say, 3. If I had to put a variable next to it, it would be 3 times x to the 0 power, right? Because anything to the 0 power is equal to what? 1, okay? So if we followed our procedure, all right, f prime would equal 0 times 3 would be 0, x to the negative 1, but what's 0 times anything? It's just 0. Okay, so that's why the derivative of a constant is 0. Okay. All righty. Congratulations, that's the shortcut. It's known as the general power rule for derivatives. Okay, it's the general power rule for derivatives, and it is your best friend, and you're going to use it a lot. Okay, you're going to use it a lot. Much better than that big, long limit definition. Agreed? Uh-huh. Yep. All right. Are there still lots of little places to make mistakes? Right? If we don't multiply correctly, we drop a sign, we don't subtract correctly. Like, there's lots of little places that we can make mistakes, so we just have to be careful. Okay? All right. So, power rule, this is what it says. If f of x is equal to x to the n. That's what makes it a power function. It's x to some power. N is a number, right? Then f prime of x is always n times x to the n minus 1. All right? That's the general power rule. We're taking that exponent, multiplying it by the coefficient in front, subtracting 1 from the exponent. So that's the general power rule. Now, the next thing we have to know is, when can I use it? All right? When do I really have a power function? All right? Because when I don't have a power function, it has different rules. Right? And we're going to find that out tomorrow. So could I use this formula on x to the third? Is that a power function? Yes, it is. Okay, that's a good one. What about 2 to the x? Is that a power function? Okay, no, it's an exponential function. All right. What about negative 3 over x cubed? It is, okay? The reason it is because I could rewrite that, do y'all agree, as negative 3x to the negative 3. Okay, I could rewrite it as a power function. So if I can do that, then it's a power function. Okay, so that's a power function. What about y equals square root of x? Yep. How could I rewrite it? X to the 1/2. Okay. So if I can rewrite it as a power function, we're good. Okay. Go through and look at the rest of those. Which of the rest of them are power functions? Hey, oh, y'all come fix my light?
Yes, ma'am.
Oh, you're my favorite. It's right there. Thank you, thank you. Yesterday we were trying to have a seizure. Today we're better.
Looks like that one went out.
All right, what do y'all think? Which other ones are power functions? 3x minus 5, good job. Anything else?
I would say like 4 square root.
Yes, the 4th root of x to the 5th. Yep, that one works. That's a power function. Anything else? Yeah, negative x to the 5th over 2. Everything else is some different kind of function. Absolute value, remember we have to treat that as a piecewise function, okay? The pieces will be power functions, all right? But it will have to be a piecewise. So we'll kind of leave it out for right now, but it is an option, okay? One thing I do want to show you, do you agree that this is the same thing as negative 1/2 x to the 5th? Okay, for some reason that confuses people, okay? There's a coefficient there that is negative 1/2, all right? And you're going to need to remember that for some of the ones we're going to do, okay? That you have a coefficient there that's a fraction, okay? So let's work through number 5 together, and then I'm going to let you guys do a couple, okay? All right, so we want to find the derivative. So find dy dx, given that y is negative x to the 5th over 5 plus 3x to the 4th over 4, all that good stuff, okay? Let's walk through our general power rule. So dy dx says we're going to take our exponent times our coefficient. So 5 times negative 1/5 would give me what? Negative 1, yeah. X is going to go to what power? 4th. Okay. For the next one, 4 times 3/4. 3. X to what power? 3rd. Negative 5/2 times 2. Negative 5. X to what power? Yep, first. And then my exponent is 1 times 2/3, which would be 2/3. X to the 0, I don't need it. Okay? Question on that power rule. All right, try the next two. Watch your variables. Rewrite if you need to start. Okay? Okay. Before I start that first one, I will always rewrite because there's radicals there. There's something in the denominator. So I would rewrite that as 3x to the 1/2 minus 2x to the negative 3 plus 5x before I started. Okay? Just so I know when I take my derivative, I've got everything written as a power function. Right? So let's do f prime. So f prime is going to equal 1/2 times 3, so that would be 3/2. X to the 1/2 minus 1 would be negative 1/2. Negative 3 times negative 2 would be a positive 6. Negative 3 minus 1 would be to the negative 4. And then 1 times 5 would be 5, and then x would disappear, right? Now, typically in math, we don't leave negative exponents, okay? So if this were on a multiple choice question, you might see it just like that, or you might see the answer written as this: 3 over 2 square roots of x plus 6 over x to the 4th plus 5, okay? Free response, they're going to take the first, all right? Multiple choice, they're probably going to simplify it to the second, all right? So just know that you may have to do some simplification, mathematical convention type stuff, okay? You don't have to do it on free response, but they might do it on multiple choice, okay? All right, and then number 7 has 2 parts, okay? So it asked me to find dp dt. That means t is my variable that we are differentiating. So dp dt would equal, that would give me 3t squared plus 12t minus 5/3, okay? Now, remember, the derivative gives me a formula for the slope of the tangent. And so if I want to write the equation of a tangent line, I need the slope of the tangent and I need a point. Okay, so anytime we want to write the equation of a tangent line, we want the slope of the tangent, right, and we want the point. Well, I know my point is going to happen when t is 3. We're going to have to find p. And I know the slope of my tangent is going to be dp dt evaluated at 3. Okay, so that's how I'm going to get those values that I need, all right? So the derivative is a formula for the slope of the tangent, okay? So let's get dp dt at 3. So we would take 3 times 3 squared plus 12 times 3 minus 5/3. Okay, do a little math. It's not going to be terrible. 27 plus 36 minus 5/3, which would be 63 minus 5/3. 189 over 3 minus 5 over 3, so 184 over 3. I don't even know if that simplifies. No, it won't. Okay, so my slope is 184 over 3. Right? If I want to know the point where x is 3, what am I going to plug this into to get the point? To plug it into the derivative or to plug it in somewhere else? The original function. So I'm going to take the p function and evaluate it at 3. So 3 cubed plus 6 times 3 squared minus 5/3 times 3 plus 16. Thank goodness we're going to lose that fraction. Okay, right? So 3 cubed would give me 27. 6 times 9, 54, minus 5 and plus 16. Just got to do a little bit of arithmetic there. I'm going to keep the 27. 54 and 16 would be 70 minus 5. Or 22 plus 70, which would be 92. So I've done a lot of math. Have I answered the question yet? No. Okay. We've not. Oh, okay. So we want to write the equation of our tangent line. So y equals, start with your slope, 184 over 3, x minus 3, and then plus 92. Okay, so that's where the derivative is going to be super useful. All right, that's where it'll be super useful for us. Okay, so it'd be nice if everything was just, hey, find the derivative, but it's not going to be. Okay, it's going to do lots of different things. All right, like that one, write the equation of a tangent line. Look at this next one. Does the curve have any horizontal tangents? If so, where? Okay, this would be on a non-calculator portion. All right, I don't know how to graph that. Right, so we're gonna have to think about what does it mean to be a horizontal tangent. Okay, if I'm horizontal, touching the graph horizontal, what does that mean my slope is? 0. Okay, so what I'm looking for is where is y prime equal to 0? That's what this question's asking me to do. Okay, where is y prime equal to 0? So what would be a good first step? Find the derivative. Yeah, let's find the derivative. We need y prime. So y prime, okay. What's my derivative going to be on this one? All right, 4x cubed. What's my next term? Minus 4x. Derivative of 2 would go away. All right. And we're going to set that bad boy equal to 0. Uh-oh, algebra. All right, we got to solve for x. What should I do first? Pull out a 4x. All right, if I pull out a 4x, at least with x squared minus 1 is equal to 0, I could factor that again if I wanted to. X plus 1, x minus 1. Okay, so where are all the places, because apparently there's more than one, where we have a horizontal tangent? Yeah, 0, 1, and negative 1. And you could write that plus or minus 1 if you want to. Okay? So that's the math they're going to want to see. Let's look at this next one. Find equation of the line perpendicular to the tangent to the curve at the point 2, 3. Right? So we want to write the equation of a line, which means I'm going to need a slope and a point. Did they give me either one of those things to start? Yeah, they gave me that point, praise the Lord. Okay, so that's one less thing I got to do, right? But I want the slope of the line perpendicular. Okay, what should I do first to find the slope of the tangent line that's perpendicular? Find the derivative first. So y prime, 3x squared minus 3. So the slope of the original tangent will be y prime evaluated at 2. 3 times 4 minus 3, or 8. What would be the perpendicular slope? Negative 1/8. Okay. So nice. Okay, so now let's write our equation. So we know our slope and our point. Y is going to equal negative 1/8, x minus 2, and then plus 3. Okay, so when I say we will write lots of equations of lines, this is what I'm talking about. Okay, and you'll be like, at one point you'll go back and be like, can I just rewrite the equation of a line, please? Right? Yes, sir. 12 minus 3, it's 9. God bless. I'm glad y'all love me enough to not persecute me. Negative 1/9. Luckily, it's an easy fix. Thanks, Jace. Those are the mistakes I make. Okay, I make arithmetic mistakes. Do what? You weren't even going to check it, right? Okay. Question about using the general power rule and all the good things. Okay. Well, let's take it a step farther. All right. Just a little bit, not a lot. Okay. And let's talk about the rules, some of the different derivative rules that we have. And by that, I mean, what if I have this function f of x that is equal to g of x plus or minus h of x, okay? We've already been doing this. We just didn't call it a rule, okay? If I took the derivative, if I had multiple things, like we had an x squared, an x cubed, and a 3x, we did g prime at x plus or minus h prime at x, okay? And that's how we use it, right? Notice, though, it's only going to work for addition and subtraction, right? So it does not work for all operations. We're going to find that out next week. Okay. I can't give it to you all at once, you know, because then what's the fun? All right, gotta have a little suspense. Okay. You've already been doing that. We just put it into some formal notation. All right. So let's take a look at this one. I really like it. This is let's get creative, okay? Because everything we know so far is a general power rule, okay? But it wants me to differentiate. If I look at this first one, what's weird about that first one? Yeah, there's letters everywhere, okay? Like, it's like alphabet soup exploded in that problem, okay? So here's what we have to recognize. What is the variable that's actually a variable that we're taking the derivative of? T, okay? So we're actually doing h prime of t. That means everything else we treat as a coefficient, all right? We treat as a number. T is the variable, okay? So t is the variable, right? So if I do h prime at t, that 1/2 g is going to stay there. 2 times 1/2 g would just give me what? 1g. T would go to what power? 1. On the second one, I have t to the first. 1 times v would be v. T would go to the 0 power. It would disappear. K is a constant. What's the derivative of a constant? 0. Okay? Now, I show you that because this is I have this on a coffee cup, by the way. G of x equals pi cubed, so g prime of x equals 3 pi squared. Okay? That is not true. What is pi? It's a number. And so what would be the derivative of a number cubed? A really big number, derivative of a really big number, which would be? It'd be 0. Okay? That is the true statement. Okay? Pi is a number. All right? So the derivative of a constant is always 0. Okay? So yeah, that's on a coffee cup. All right? That I have. Because, you know, math nerds need math coffee cups. All right? What's wrong with the second one? There's a lot wrong with that, Ms. Moore. Come on now. First of all, it's a rational function, and we've not talked about that, okay? But could I rewrite this as a power function, power rule? Yep, I got a monomial down there. We can divide everything on the top by x squared, okay? So 3x to the 5th divided by x squared would leave you with 3x to the 3rd, okay? 2x divided by x squared would leave you with 2x to the negative 1. Negative 7 divided by x squared would be negative 7x to the negative 2. Okay, so just rewrite it as a power rule. So then y prime would be 9x squared minus 2x to the negative 2 plus 14x to the negative 3. Right? So you're going to have to get creative sometimes. Right? Yeah, I'm showing you lots of different examples. Okay? Because they can ask lots of different questions. All right, rock and roll. Here we go. Let's look at this bad boy. What's wrong with this one? Based on what we've been doing. It's a product. Yeah, it's a product, okay? But it's just distributive property. Can I fix it? Yeah, fix it. Fix it and take a derivative. Go. All right, how'd you do? Okay. All right, 13. You know, okay? Wouldn't be calculus if we didn't throw a table in there. It's what we do, okay? We got to show you all the different representations. So we want to figure out what K is, giving all of this information that we have in the table, okay? X is 16. F prime at 16 is 4/3. G prime at 16 is negative 10. H prime at 16 is pi. Not sure we'll need all that information, but that's what they gave me, okay? Now, the one thing I noticed is that I've got a square root function in there. So before I start, I'm going to write this as 3k f of x equals, fire safe matches, minus 8x to the 1/2 plus g of x, okay? So I'm going to do that on purpose so that I've rewritten my original function, okay? And I want to find a formula for h prime at x, okay? K is a constant that we're looking for, all right? So we're going to keep that, but what would be the derivative of just f? If I have f, its derivative I would write as what? F prime. We don't have a function, okay? So we would just write it as f prime. The second one, the second term, I do have a function. I can take its derivative using the power rule. So 1/2 times negative 8 would give me what? Negative 4. X to what power? Negative 1/2. Don't have a function for g, but derivative of g I would write as g prime, okay? We want to evaluate this at our x value of 16. So looking for h prime at 16 would equal 3k times f prime at 16 minus 4 times 16 to the negative 1/2 plus g prime at 16. So some of this we're going to pull out of the table. Some of it we're going to do arithmetically by ourselves. Right? Using the table, what's the value of h prime at 16? It's pi. We're going to keep our 3k. What's the value of f prime at 16? 4/3. All right, this one, a little tricky. This is 4. 16 to the negative 1/2 would be square root of 16 in the denominator, right? So 4 over the square root of 16, 4 over 4, which would just be 1. Okay, minus 1. And then g prime at 16 was negative 10. Right? We're trying to solve for k. Right? We're trying to solve for k. So I have pi equals 4k minus 11. Or k is going to equal pi plus 11, all divided by 4. It's a crazy number, but it is a number. Okay, what questions do you have about that one? So using a table, they will do those. All right, you can count on it. It could be both. Could be both places. Yep. All right, so using that table. Okay, let's look at that next one. Determine where, if anywhere, the tangent line is parallel to this line. Okay? If it says something about a tangent line, that should be your first hint that I need to take a derivative. Okay? If you see tangent line, you know nothing else, take a derivative. Okay? So what's going to be the derivative of f of x? Three x squared minus 10x plus 1. Okay? We know that's also an equation for the slope of my tangent. Okay? They're the same thing. I want my tangent line to be parallel to the line they gave me. What's true about two lines that are parallel? They have the same slope. What's the slope of the line they gave me? -2. So in other words, I'm looking for where is f prime equal to -2. That's the equation we're going to solve, right? So I'm going to take 3x squared minus 10x plus 1 and set it equal to -2. Or 3x squared minus 10x plus 3 is equal to 0. I'm going to pray I can factor it. 3 and 1, we'll make them both negative. Yep, so I get 3 in the end and 10 in the middle. All right, what are those x values that are going to work? So a little algebra, 1/3 and 3. Okay, question about that one. Again, very seldom do you have to say one-dimensional question, all right? Occasionally you will. It'll just be find the derivative, all right? But a lot of times it's going to have something like this in it where it's going to test multiple concepts, okay? All right, let's take a look at this one. This is a calculator active question for a reason, okay? So they've given you a bunch of stuff here. It gives you a table with certain values for x, certain values of f at those x values, and certain values of the derivative. If you read in the question stem, it also tells you that h of x is this nasty function, x squared e cosine of 3x. Okay. So it says let m be defined by m of x equals f of x plus h of x. Find m prime at 3. So in other words, I need to find m prime to start. Okay. Well, that would be f prime at x plus h prime at x. Pretty straightforward. Okay. Where it gets a little weird is that it wants me to find m prime at 3. So that'd be f prime at 3 plus h prime at 3. Well, f prime at 3 they gave me. It's in the table. Okay? So f prime at 3 is just 8. Okay? But to get h prime at 3, we're going to have to math 8 that bad boy. Okay? That's why it's on a calculator section. You don't know how to do that derivative yet. You will. All right? But you don't know yet. Okay? So we would put it in math 8. So math 8, my function would be x squared e cosine 3x at x equals 3. How many decimal places are you going to take? 3. All right. I think I get negative 2.061. F.938. Okay. Question on that one. All right, let's do a couple more. All right, so just trying to show you lots of different variations here. All right, lots of different variations. Ooh, I love this one. They're going to give you a graph problem. You can count on it. All right, so it says the graphs of the linear functions f and g are shown. All right, h is f of g plus g, f plus g. Find h prime. Well, that means f prime, h prime is f prime plus g prime. Okay. Now, if I have a linear function, what's the derivative always going to be? It's a constant, okay? It's just the slope of that line, okay? So my derivative of any linear function is the slope of that line because it's going to be a constant, all right? So let's look at the F line. Let's see if we can find the slope. Pick you a couple points that cross nicely. Okay, what appears to be the slope of F? Yep, 1/2. And then let's find the slope of G. Looks like it's -1 maybe. And so then f prime plus g prime is just going to be 1/2 minus 1, which is -1/2. Right? So using what we know about linear functions having constant slope. All right. Love this next question. Love, love, love. Okay? Put a star on it. You will see it again. All right? You will see a question like this next one, 17. What values of A and B would make the function, and it gives me a lot of stuff there, differentiable at x equals 3? Okay? What would make it differentiable? Right? In order for it to be differentiable, my left and right derivatives would have to be equal, right? They would have to be equal. So let's do the top one, okay? So the top piece, f prime at x, would equal 2x minus a. The bottom piece, f prime at x, would just equal 1. So do you agree with that? Okay, it would equal 1. Now, something else that we have to consider, all right, something else that we have to consider is we got to think about continuity, all right? Because if it's discontinuous, because it didn't tell me it was, I couldn't be differentiable. So let's talk about continuity. Okay. If I'm doing continuity, the first thing, f at 3 has to exist. Which piece are we going to use? Yep, that bottom piece. So it would be 3 plus b. Okay. Part 2, we would look at the limits. So the limit as x approaches 3 from the left of the top piece, x squared minus ax plus 2, okay, is going to have to equal the limit as x approaches 3 from the right of x plus b. So let's evaluate those two limits. We're just going to plug in. So that would give me 9 minus 3a plus 2 and 3 plus b. All right. Now, in order for it to be continuous, what has to be true about these two limits? They have to be equal, okay? So 11 minus 3a has to equal 3 plus b. Right? So everybody agree with that? Right? And then over here on my differentiable part, those two derivatives have to be equal, all right? So 2x minus a has to equal 1. Well, what x value are we considering? 3, so we're going to plug that in. So 2 times 3 minus a would equal 1. 6 minus a would equal 1. And so a would equal 5. Right? So we're doing kind of a nifty system of equations here. All right, doing our differentiable piece. Then we're going to go back and use our continuity piece. So if we found a was 5, let's put it over here so we can find b. Right? So 11 minus 3 times 5 would have to equal 3 plus b. 11 minus 15 would equal 3 plus b. Negative 4 would equal 3 plus b. And so b would be negative 7. Right? So you had to use both definitions because we just had too many variables. Okay? They didn't tell me anything about continuity. If they did, we could have gone straight to the limits. If they said, hey, it's continuous, all right, then we could have gone straight to the limits, okay, the left and right limits there in continuity and gotten that equation. Differentiability, we're going to take the derivative of both pieces. Those two derivatives have to be equal as well. Otherwise, we get that cusp or corner situation going on, okay? And then we just have to solve it out so we can find one of them. Good question. All right, lots of calculus in that question. Now, 18 is just for fun, all right, just a little extension, all right, just a little extension. This time, they tell me the derivative and ask me what could the original function have been, all right? Can we think backwards enough to figure out what the original function would have been? And I'm actually going to fix this over here. I'm going to rewrite this for a second. So f prime at x, 3x squared minus 2x plus 5 plus 1/2 x to the negative 1/2, okay? Let's see if we can think backwards to figure out what f would have had to have been to give me those terms above, okay? So to get 3x squared, what would I have had to started with? X to what power if I took a derivative and it took it to the second? Cubed, okay? The coefficient works, right? That gives me 3x squared, so that's going backwards. All right, I got a minus there, so I'm going to need a negative. I have x to the first, which means I had to start with x to the second. Does that take care of the coefficient? Yep, derivative of x squared would be 2x. What would I have to start with to get a plain 5? 5x. Okay. This one's a little bit harder, okay, because I got an x to the negative 1/2. All right. What would I have had to start with? 1/2. Okay? So that was just for fun, right? This is called an antiderivative, what we just did. Okay? They give me the derivative and I go backwards. All right? So just a thinking exercise, going forwards and backwards. Just so you know, after Christmas, all we do is go backwards. Okay? So there you go. So we're going to go forward for a long time. All right? Then we're going to go backward. All right? All right, your lesson practice. There is a worksheet back there, 2.6. Has lots of really good problems on it that are kind of outside the box, more AP-esque. On page 129 and 130, here's some good ones to look at, 3, 5, 7, 9, 37, and 39. Okay? Your, go ahead and do your wrap-up for me really quick on Google Classroom. It's a quick one. And Wilbur, I lied to you. We do have a quiz on Friday, but it's just a quiz for just section 2.4, which is continuity and differentiability. It's only got like 5 questions on it, I think. And I have not graded the other one, but that's on the agenda for today. Yes. Because the derivative of x, b is a constant. Derivative of x would just be 1. Because you have an exponent of 1, 1 times 1 be 1.